The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Today, we're going to talk about synchronization, how all these different nodes on the network come to consensus, how they link up. So it's sort of bringing it all together. So far in these lectures, we've talked about signatures, mining and blocks, transactions and scripts, and now we're going to put it all together. Okay, how does this all actually work? What do all these components come together to do, and how does this make, this cool money? Quick recap on signatures that I think you got the idea from the homeworks, from the lectures. You have these public and private keys. This key pair where you generate the private key, you distribute the public key. The private key can sign a message, and anyone can verify given the triple, public key, message, signature group. This is useful for lots of things, providing identity, ownership, all sorts of things. And it's better than paper signatures, right? Paper signatures don't really sign the message, they just sort of sign the paper. So if you change some part of a document, the signature still sort of looks okay. Maybe you can see, you want the paper to not be tampered, but you can sign a blank piece of paper and then add all this text on afterwards, right? You can't do that with these systems. So signatures are really cool, and they are sort of a necessary thing for this network to work. Okay, so mining and blocks, I think you sort of got the idea with the Lamport signatures. If you've looked at the current problem set, it makes a lot of sense. You change a nonce, hash a bunch of times. Well, you change the nonce a bunch of times. Try to get a low output. Okay, so you get the idea of mining, right? You're proving work by repeatedly going through different nonces, trying to find a certain hash output that there's no shortcut to. You just have to guess and check. And now if you include the previous data as part of your input to that hash function, you can make a chain of work. And that's what we call a blockchain, I guess. Any questions on this so far? It's a basic idea from 2 lectures ago, right? Cool. Okay, and a recap of what Neha said yesterday. There's transactions and scripts. I'm not going to go into scripts too much yet, because in practice, 99% of the scripts are just checking a public key signature, right? You can do all sorts of other crazy things with the scripts, but almost nobody does yet. Basically, they just say, okay, I'm sending to a public key hash. When I spend from it, I reveal the public key, check that the hash matches, check a signature. And transactions have inputs and outputs. We went over this yesterday. Just to sort of real-world numbers, this is how big things are-ish. So a transaction ID and index, to point to a previous transaction. The transaction ID is 32 bytes. The index is encoded as a 4-byte, so 32-bit integer, which is kind of overkill because I think the most that there's ever, the most outputs there's ever been is like 1,000 or something. So you really don't need it to be able to go up to 4 billion. But that's how it is. The signature ends up being about 100 bytes because you have to provide the public key, which is either 33 or 65. And then the signature itself is encoded to something like 70 bytes. Both of those things could be much more efficient, but they're not yet. And the output is actually a lot smaller, right? An output, the script, the main thing is your public key hash, which in Bitcoin is 20 bytes. And then you have those other little opcodes, which adds a few bytes. And then your amount, which is, so all amounts in Bitcoin are encoded as 8-byte signed 64-bit integers. So you can have like pretty high precision. And that's also overkill, since all the Bitcoins ever mined put together in one, if you added them all up, it's nowhere near 64 bits, right, 2 to the 64. It's like 2 to the 40 something, I don't know. So it's also kind of overkill, but yeah, whatever. So this ends up being, for a 1 input, 1 output transaction, less than 200 bytes. Okay, so that's a message, pretty small. You can broadcast it around the network. Inputs point to old outputs, have signatures, outputs have scripts and coin amounts. Yeah. Okay, so what do we do with all these things? What is the mining process? So in the homework, you're mining your name, right? You connect to the server, figure out what the last block was, put your name on, put a nonce, and continue to mine. That's not super useful unless you want to like prove that you're, hey, this was me. In Bitcoin, the basic idea is users are making these transactions. Transactions are moving coins from one place to another, from one key to another. They make the transactions, they sign them, and they broadcast. I'll get into what broadcast means. So in the current problem set, there's one server, which is not really a robust distributed system, as people may have seen yesterday from about 1:30 to 3 p.m. when the whole thing went down. In Bitcoin, it's completely peer-to-peer. Every node is the same. They're all listening for people connecting in. They're all connecting out to other nodes. So broadcast, and they broadcast. So if someone sends you a message, you'll pass it on to all the other people. So it's called a gossip network. In practice, it works okay. It's fairly heavy load on some network traffic, but you can make transactions, sign them, broadcast them. And then someone, the miner, takes all these recent transactions that they've seen and puts them into a block and then does some work. So those transactions are now confirmed, and people can build the next block. So the only difference from the current problem set is instead of putting your name in, you put you can put your name, but you also put all these messages that you've seen recently, and so you commit to them that way. You could do it by just sticking them all in, but instead, there's a bit more advanced way to do it. You use what's called a block header. So yeah, the block header itself is the message. So similar to the problem set, it's the block header that you need to hash to get a low output value, not the block itself, which is kind of interesting. And the headers have a hash of all the transactions in the block. So you don't just put all the transactions into one big, megabyte data structure, hash the whole thing, and then try to get a low output. You actually do some intermediate steps first. And what's interesting is it's actually just the headers that make a chain, not the blocks themselves. So instead of blockchain, you could call it a header chain. Okay, so I'll talk about headers. The headers are 80 bytes, and they're actually quite similar to the blocks in problem set 2. So the main three components are, you've got the previous hash, the Merkle root, and the nonce. And so this is like in the problem set, right? You start with the previous hash, then you have a data that you're actually committing to, and then you have some data that doesn't have any actual meaning, right? Just to get the work done. So I can, to reference, if you look through the work people are doing right now, this is all public, the current problem set. There's a previous hash, which is basically the hash of the line above it. And then there's some data you're committing to, in this case, people's usernames, and then some, non-meaningful data here with, just random numbers and stuff, looks like. So very similar. Okay, any questions about this idea? Okay, cool. Yeah, so we use a Merkle root, which I think I talked about last week, Monday. Instead of just concatenating all the transactions and hashing them in together, you could do that. Actually, it would work. It wouldn't make a huge difference. But this is a little nicer if you want to prove that a transaction was in this block without giving the whole block, right? So the idea is, I have these TXIDs, and a TXID, transaction ID, is just a hash of the transaction. Stick it all, stick all the components of the transaction into bytes, hash that, and you've got what's called a TXID. And that's how you refer to transactions. You hash these two together to get this intermediate point, do the same thing up to the root. And so you can't change any of these little transaction IDs without changing the Merkle root. So it commits to all the transactions just the same way it would if you just concatenated them all together and hashed that. So we'll go into later why this is useful, but in many cases, it really doesn't help too much. Okay, any questions about Merkle tree? Good. Okay, so the actual Bitcoin headers, which many things use, has a couple fields. Some of them are actually not very useful. But the main two are previous hash Merkle root nodes, right? And then I'll talk about the other things. So there's also a version field right at the beginning. It's 4 bytes. It indicates block version. It's not clear what that's going to be used for in the future. It used to be used for sort of signaling protocol changes. I'm not sure that's going to be the case going forward because it didn't really work very well for that. So right now I think they all start like 0, 2, and then a bunch of zeros. And that's the current version, whatever that means. And if you mine something with a different version, everyone will accept it, but there'll be like these warnings that show up in your Bitcoin log files that say, warning, unknown version, unknown version detected. The idea is maybe, well, if the version increases or changes, maybe there's some new rules in this system or new opcodes or new something going on, and you're not aware of it, so you might need to upgrade your software. That was the idea anyway. In practice, what happens is you'll see in your logs all the time that like unknown version detected, and it's just someone just set random numbers in the version field, and it doesn't seem to mean anything. So not super useful. Previous hash, just like in the problem set, it's the hash of the previous block, 32 bytes. Merkle root, as described a few slides before, hash of all the transactions in the block. Time, actually kind of complex. I'm not going to go into the whole thing right here. So far we haven't really talked about time. Does anyone know why we'd want time in these headers? Yeah.
You had mentioned earlier that you don't want to accept blocks between a certain interval if they were too late.
Right. So it makes sense intuitively that like if someone says, hey, I mined this in 1987, it's like, well, that seems crazy, right? Or if someone says, here's a block, it came out in 2046, like this doesn't make any sense. So intuitively, yeah, like you shouldn't accept things that are like have some crazy date that's clearly wrong. But why? Why do we need time at all? Yeah.
You want to lock a transaction until a certain time?
Okay, yeah, you could say, here's a transaction and I don't want it to be valid before August 1st. And so then you could say, if it comes, if it goes into a block and that block has a timestamp before August 1st, consider the block invalid. You could. You can also do time stamping based just on block height. But what's the main, does anyone know the main reason to like have height here? Yeah.
Is it because if they're like competing transactions and then you would pick one or the other?
So the competing transactions, when they sort of get into a block, and that sort of solves that competition, right? So you have two transactions that both are mutually exclusive. Well, if they're both in the same Merkle root and both in the same block, then that block is considered invalid. Because it's like, hey, you've given me a block, it's got two things that can't both exist here. So throw the block away. If you find two blocks that both seem to have, that sort of collide, they're both pointing to they've both got the same previous hash, right? So they're both in the same height, we call, of the chain. You could say, oh, well, whichever one came out first, right? I'll look at the timestamp and say, okay, the block that came out first will be the valid one. But the problem is, this is claimed block creation, right? You can put whatever 4 bytes you want in there. And so you can always say, oh, I just mined it exactly 1 second after the previous block. It just took me a while to, broadcast it. So you can't really trust the timestamp to see which came first. If you could, you wouldn't need all this crazy mining stuff, and transactions themselves could just have a timestamp, and you wouldn't need this whole structure. So the fundamental reason you're mining is we can't trust people to say when they did something, right? If you can always say, no, this transaction came first. No, this came first. So the real reason for this blockchain is, okay, we know which came before what. So, yeah.
In practice, which one happens? Do people just lie and say it happened a second later, or is it the actual creation?
Oh, in practice, the timestamps are pretty unreliable. They can be off by minutes. It can be before the previous block's time, and that's okay. It seems intuitively like, well, that should just be a rule, And it would have been cool if it was a rule and made things simpler from the beginning. But if you're pointing to a previous block, I'm building on top of it, and the previous block came out at 10:15, and I set my timestamp to 10:12, 3 minutes prior to the previous block. Logically, that's impossible, right? I'm referencing something and I'm saying I'm coming before it, but the software says that's okay.
So for creating a new version, would it be useful to just get rid of version and time, like for creating a new blockchain?
So version, maybe you could get rid of, or you could put it somewhere in the Merkle root or something. Time actually does have a really useful purpose. Does anyone, maybe if you know, yeah.
I mean, I don't know, but does it play into the difficulty of the mine, does it?
Yes. Yeah. So the main reason for time here is to adjust the difficulty. And that happens every 2016 blocks. You just look at, okay, how long did this 2016 block period take according to these timestamps? And if it took 2 weeks, okay, we're good. The difficulty doesn't have to change. If it took 3 weeks, that means the blocks were coming out very slowly, and we need to reduce the difficulty. If the 2016 blocks came out in 1 week, that means, wow, people were mining really fast. And so we need to increase the difficulty. So there's this negative feedback mechanism based on this time. And it can be tweaked, right? It's not accurate. You can have things coming in the wrong order. The general rule of thumb the rule in the software is about 2 hours. If you see something that's 2 hours off from what your internal clock says, you will reject it. But that's a huge gap, right? Most network systems, everyone's got their clocks to the same second at least, or millisecond. That's 2 hours is like kind of enormous gaps. But the system works okay because you've got these really long-term difficulty adjustments that only happen every 2016 blocks, which in practice is something like 2 weeks. So if someone gets something a few minutes off, it doesn't really affect things too much. And it's really only used for, okay, look at the last 2016 blocks, 2 weeks-ish of work of all these blocks and see how fast we need to make things. So that ties into the next field, which is difficulty. It's in a sort of weird floating point-like format with a mantissa and exponent, which is totally custom, and you kind of have to write your own code to deal with it. But it basically says, okay, what does the hash have to be below? It's not just number of bits. So in the problem set, I said 33 bits of work, right? So that's fairly easy to detect because you just look for 33 0 bits in the front. In Bitcoin, it's not just number of bits, it's actually a number that must be below. If it were just number of bits, the problem then is your adjustments are fairly coarse because you can only adjust by a factor of 2, right? You can double your difficulty or halve it. But with this, you can have much smaller difficulty adjustments of like a fraction of a percent. This field is pretty much useless since you can calculate it from the time fields of the previous blocks. So you could just have it be implied, but it's in there, and you just whatever. It's an extra 4 bytes. I don't think you actually you don't have to store it on a disk if you want. Because you can just figure it out from the other things.
Wouldn't you need it for an SVD wallet? Well, it's not official.
No, because you can figure out what difficulty is just from the headers, right? So, I mean, it's in there. I guess it's nice if you just want to validate whether a single header has enough work, but it's like how much work does it claim it needs, and then you can validate it. But I don't know, it's in there. It doesn't. You could take it out and reorganize the code a little if you wanted to optimize it, but that would change so much that no one bothers. Yeah.
So when we talk about adjusting difficulty and even just like issuing like the problem or proof of work, who issues these, like for the problems that we go to the central server, but
Right. So in this, it's just everyone broadcasts their blocks. So if you've received a block or if you found a block yourself, you just send it to all your peers that you're connected to. And so there's no like, oh, this is the canonical block. There can be competing blocks where you have 2 at the same time, and just stochastically, one of them will pull ahead because of more, randomly. So you can have conflicting things. Yeah, and then the adjustments also, everyone computes the adjustments. So and this is actually very quick computation because you're not even looking at 2016 timestamps. You're basically just saying, okay, if so height is just what block number it is, right? So if right now it's about 500 million, right? No, sorry, 500,000. So you basically in the code just say, well, if height modulo 2016 is equal to 0, check the 2006, check height minus 2016's block, compare the two timestamps, subtract them, get a duration, and then compare that duration to 2 weeks, and then change the difficulty proportionally. So it's actually like super quick for everyone to compute the new difficulty, and they only do it once every 2 weeks. And it's pretty straightforward. There are like weird attacks and stuff, and it's kind of some weird off by one errors where I don't remember. Like it's kind of confusing. It's also confusing because the test network, which I haven't gone into, but we'll use probably next week or in 2 weeks. There's a Bitcoin test network, which operates pretty much exactly the same as Bitcoin, except everyone agrees that the coins are not worth any money. What's interesting is it's actually called testnet 3. The first two test networks had the same setup. However, the agreement that they were not worth any money broke down. So at testnet 1, someone said, hey, I'll pay you a Bitcoin for 1 million testnet coins. And once people saw this happening, they said, oh, well, you just ruined testnet. Now they're worth money. So we'll go to testnet 2. It happened again. Testnet 3 has had some staying power. I think people realize that if they try to buy testnet 3 coins, everyone's going to leave and go to testnet 4. So it's kind of a fun. I'd actually be okay with testnet 3 coins being worth money because I have many thousands of them. But yeah, and so one difference, guys, could you, one difference though between the test networks and the real network is the difficulty adjustments. So I think in the first test network, it just worked exactly like Bitcoin. But one of the problems was people would mine and the difficulty would increase. And then people would stop mining. Say, oh, I'm going to test out my mining software. Okay, I'll mine a couple thousand blocks. Maybe it only takes me a day or two to do so because I have a very fast computer compared to the rest of the network. And then I say, okay, well, it works. Cool. I'm going to go to the real network now. And I leave the test network. And now the difficulty increased because let's say 2,000 or 4,000 blocks came out. And they came out very quickly, so the difficulty went up. And then all the mining power left, and so now blocks aren't coming out. And since the adjustment can be up or down, but happens based on number of blocks, not based on time, if you have a very high difficulty and a very low hash rate relative to that difficulty, it can take weeks or months or years for the difficulty to reduce. So testnet 3 put in this sort of difficulty nerfing code, which is probably wrong and not what they intended. And it has this thing where like if 20 minutes have gone by, the difficulty lowers, and it's kind of ugly. So that's the main place I've dealt with this field. One other rule with the restriction. The difficulty can go up by at most a factor of 4 and drop by at most a factor of 4. So if you mine 2016 blocks in one day, the difficulty goes up 4x, but does not go up 14x or whatever the implied would be. Okay, yeah.
Is it difficulty constant for 2 weeks then?
Yep. Well, sorry, not 2 weeks, 2016 blocks, which is generally around 2 weeks, but yeah.
From blocks to block, within like almost 2 week period, that difficulty would be the same.
Yeah, so if you actually look at the headers, like this is just the constant, it just is always the same. So it's kind of a silly field to be in there. You never need it, and it's always the same, so yeah. Any other questions about, yeah?
How many transactions are usually in the block?
Oh, I'll get to that. Right now, a couple thousand, 4,000-ish. We'll get to that, I think. I have that. No, but yeah, in the Merkle root. So the height of the Merkle root's like 12-ish, right? And it goes out to maybe 4,000 transactions. Sometimes more, sometimes very few. You'll find empty blocks that just have one transaction in them, and that transaction ID just becomes the Merkle root because it's like a height 0 Merkle tree. But yeah, something like that. Okay, and then last, pretty easy. There's a nonce, 4 bytes. Anything you want goes in there. You could think of it as a uint 32, but it's there's no meaning to it. Okay, so does anyone see a problem with this nonce field? Yeah, yeah, it's too small, right? 4 bytes. Even in the homework, people are using 12 something bytes for a nonce. With only 4 bytes of nonce, you can go through 2 to the 32 possibilities, which is not enough to mine in almost all cases, because you're going to need to go through 2 to the 70 possibilities to find a block. So what are some ideas for how do you deal with this problem? Like it would be nice if it was just 8 bytes. That'd make things simpler. But the system is what it is. It's very hard to change. How, as a miner, would you work around this issue?
Adjust the version, time.
Yeah, so you can adjust version. So that may be why sometimes weird version numbers come out. Time is a good one too, since time. Yeah. Sorry. So yeah, adjust time and also Merkle root. So time, if you're off by a few seconds, nobody cares. So use the low bits of this time field as part of your nonce. It's kind of in the wrong place, but you can make chips to sort of twiddle these bits as well. What's also nice is that every second you can you can do it the wrong way, right? And you can say, oh, I'm just gonna take the least significant 4 bits of my time field and just use them as nonce space randomly. What's nice is that the actual time progresses by 1 bit every second, right? So as long as your chip has enough space, right? So you're like, okay, I've got 2 to the 32 here, another 4 bits here, so I'm at 2 to the 36. If your chip only goes through 2 to the 36 hashes every second, you're good, right? Because the actual time progresses. The other way you can do it is modify the Merkle root. And you can do that. So can you think of ways to modify that without breaking things?
Add or drop transactions.
Yeah, you could add or you could drop a transaction. So you say, okay, I have all these transactions, I'm going to drop one. That's got some disadvantages because it may pay fees to the miner.
Changing the orders.
Yep, you can swap them. You can just go here. You can just say, okay, well, these 2 are independent. I'm going to swap them. This will change, which will change that. So you can swap transactions around. You can also edit what's called the Coinbase, which I think is in like one more slide. Yeah, so there's a bunch of ways that you can change things. And so this is really where you're going to have all the variation, right? You have 32 bytes here. So, and just even if it was just swapping, and if you have 1,000 transactions, swap in whatever order you want, there's enough sort of entropy there that you'll be able to find it. So what's interesting is that the nonce is there, and it's important because that's where sort of the high speed mining occurs. But most mining chips will also have circuitry to modify this because they're operating so quickly that they will exhaust the 4 byte nonce space in a fraction of a second. And so they'll have to swap 2 transactions, recalculate a Merkle root, which involves a few dozen hashes, and then go back here. So it actually doesn't hurt their efficiency too much because, okay, I just did 4 billion hash operations, and then I need to do a few dozen more to get to the next 4 billion. So it doesn't hurt things too much. Also in Bitcoin, sort of weird quirk, it's called SHA-256D. They do SHA-256, and then from the output, they do SHA-256 again. Not sure why. I think in one person's first problem set, they inadvertently were doing the same thing. And it's like, yeah, that works. Satoshi, whoever he or she was, or they, just put that in there. Any questions about this header and this format and anything about it? It's pretty compact, right? It's 80 bytes. Yes.
Including the Merkle root. So obviously if you end up mining something, you don't have to put anything there. So the only incentive is the transaction fees. So
and the block reward, which I'll get to in a second. But yeah, you That's a good question. Can you put nothing in as a Merkle? I don't think so. I'm pretty sure you need one
Or it's
transaction.
like, I mean, you need the base, well,
That's-
even if you just did the Bitcoin-based transaction, whatever.
You can do that, and there's many blocks. So in the first year or so, in 2009, almost all the blocks are empty and only have one transaction because no one was using it, but people were mining. So it was very similar to the problem set where everyone's just mining and they're not actually using the system.
But then
Right now, there's
people aren't
thousands.
doing that just because there's transaction fees.
Right
Is that the
now-
only incentive? Like, people just decided.
No, you still get more Bitcoins, right? So you still get a reward. The reason you'll see empty blocks now is a little tricky. We're not sure, right? Because who knows? But it's probably because of blind mining, where you receive a block and you haven't actually looked through the contents of the block yet, but you want to mine the next block. But you're not sure what transactions to put in. You see this 80-byte header, and you're like, oh, someone found a block. But you only have the header, and you want to build on top of it. Because you have a bunch of transactions you'd like to put in, but they may have already been put into the previous one. And so you're like, well, I have no idea what's in the previous one. I'm just going to mine a block with nothing in it. That way I'm sure that I'm not going to conflict with my previous one. So you'll often see it. You'll often see a block with only one transaction very soon after its predecessor block.
Right, so like every once in a while, it would check. So you're saying like if it happened to win the block really quickly,
Yeah.
there's more likely to be one transaction.
Right. Because a miner might. It's actually an optimal strategy for a miner to say, look, first thing I'm going to do, download the 80-byte header. I'll figure out if it's got a valid proof of work. If it does, I'm going to just assume it's valid for the next few seconds because it probably is. And then I'm going to try to mine a block on top of that. Reference this previous block, mine a block on top. The thing is, I have no idea what's actually in the block. I have no idea what contributes to this Merkle root because I haven't even downloaded that data yet. But I can build on top of it just from the header, but I can't include transactions because I have no idea what transactions are in here, so they might conflict. So I'll just mine sort of blind for a second or two, and then I download all the stuff, download all the transactions, validate it, and now I can include my transactions that haven't been included. And so that happens. It can be an okay strategy. Sometimes it can lead to you mining an invalid block, right? If someone produces an invalid block and you just see, oh, well, it's got proof of work, you grab that header, start mining on top of it. No matter what you mine, it's going to be invalid, right? Because it's pointing to an invalid block. That happened 2015 or 16. In the summer of 2015, it happened, and it was like quite extensive. It was like 7 or 8 blocks in a row that were all invalid because none of the miners were actually verifying anything. They were just downloading the headers from each other and being like, yeah, I mean, he did the work. So they were just assuming everyone else was verifying the Merkle roots. And yeah, so then it ended, so they lost 25 times 8, however many Bitcoin, they lost, hundreds of Bitcoins, which at the time was still worth quite a bit, and now is worth, millions of dollars, just because they weren't actually checking things. Yeah.
If I mine a block and it's empty, do I decrease my chances of being mined afterwards?
No. Actually, I would say you would, sort of game theoretically, you would increase it. Because you're not depleting the mempool. Which, okay, I need to talk about the actual mining Coinbase and mempool and stuff. But yeah, it's a tricky question. I'll try to get back to it. If I don't, bug me again. Okay, TX, so in this Merkle root, right, you've got all these transactions. They have a specified order. Transaction 0 is the Coinbase transaction, and it's special. It generates new coins, and it takes fees from all the other transactions in the block. I think Neha mentioned this yesterday, where if you have a difference between the input amounts and output amounts, that's implicitly a fee, right? So if your inputs, right, so here, Neha's thing, you're spending 20 coins, you've got 5, 10, 4. Okay, well, there's only 19 coins in the output, so there's an implicit fee of 1 coin. That 1 coin can go to transaction 0, right? So transaction 0 has essentially no input. Transaction 0's input field is just empty, anything you want to put, any bytes you want to put in there. Its output field generates new coins. So that's currently 12.5 coins. So currently, if you mine a block with only TX0, you get 12.5 coins. If you mine a block with thousands of transactions, you get the 12.5 coins plus the difference between the input and outputs of all the other transactions in the block, which can be even more than 12.5, which can recently, like in January, December, there were quite a few blocks where they're getting 25, 26, 27 coins because the total fees for the entire block were more than 12.5 coins, which is, you know, hundreds of thousands of dollars now. So it's kind of cool. The fees have since decreased. Fees are highly variable, and we'll talk about fees in a few more lectures. And it's kind of a mess, and but it's an evolving area in this whole network thing. So you got your Coinbase transaction. That's important. That's why people are doing this stuff, because they want money. All the other transactions can be shuffled around. However, they can only spend outputs from previous transactions. And previous means they have an index within the block that's lower, right? So for example, you have transaction B spends an output of transaction A. Transaction A must come first in the block ordering, right? This makes it so that you can go through in a linear fashion and validate every transaction in order. Otherwise, you'd say, go through, see, okay, transaction 0, I don't have to validate that, that's Coinbase. Transaction 1, transaction 2, and then you see transaction 3, it appears to be spending something you've never heard of. So that would, at first, that would appear to be invalid. And then maybe you go through another few transactions, say, oh, this creates the output that this thing I just saw before spends. It's sort of out of order. It makes things very complicated to validate. And so this rule ensures that if you go through and just check every transaction in order, it'll all make sense. Yes?
Is there any benefit of being earlier or later?
In the block?
Yeah.
No, I don't think so. I mean, I can't think of one. Yeah, I mean, it's just sort of random. A lot of times they'll organize it by fee rate, or by default they'll just organize it by when they saw them first. So it's pretty arbitrary.
Does that mean that you have to wait until the transaction that contains your output has been mined in order to spend that again?
No. Although, if they did, that would make the software a lot simpler and easier to deal with, but that is not how it works, right? So you can have, for example, I'll draw it. You can have a block where there's, let's do it this way. So you have TX0, there's Coinbase transaction, transaction 1, transaction 2, transaction 3, and transaction 3 may be spending something that was generated in transaction 1. That can happen, right? So if you make transaction 1, broadcast it, it's unconfirmed. You then make transaction 3, broadcast it, spends transaction 1. The miner can put those in the blocks. They must put it in order, right? So if this happens, you can't switch them in order, but that's considered okay. It makes it makes multi-core validation more annoying, right? If you said no, you can only use outputs that have already been confirmed, then the block validation becomes embarrassingly parallel because you can just validate every transaction independently. That would be kind of nice. There's other interesting reasons why this is also useful. So, I mean, if I were designing it, I would say you have to do confirm because it just makes things simpler, but I was not Satoshi. So yeah, the order is fairly arbitrary. Any other questions about block ordering, Merkle root stuff? And then we're going to have a quick intermission right at the halfway point. Sounds good? Okay, so 256-second break. Okay, so now I'll talk about the synchronization process. How does this actually work in the software when you download Bitcoin? So first, you download Bitcoin. You go to bitcoin.org, your friend hands you a USB drive and says, hey, I got some good stuff, man. This new thing called Bitcoin. And so you've got the Bitcoin exe file or DMG file or the binary or the code. And you want to know what's been going on for the last 9 years. So first, you download the binary or you compile the code. And you verify all the GPG signatures of this code, right? If you want to do this securely. So I'm sure everyone has their PGP keys on the MIT PGP server and goes to key signing parties out on the weekends, right? Yeah, no? Keybase is also useful. Yeah, so I have my PGP key hash on my business card. I don't think anyone's actually ever used it. But the Bitcoin nerds actually do this, and they're very like sort of annoying about it. Because a really good attack vector is to get someone to download compromised Bitcoin code. It's like the best attack vector ever if you're trying to, do something sneaky, mainly just to steal all the money. If you get them to download a Bitcoin binary that you control, that you put some backdoor code in, the code can be like 2 lines. It's like, open a TCP connection to my computer, send me all the private keys, we're good. Or if you want to be more sophisticated, every time they click send and like type in their password, I just change all the addresses and all the outputs to me. And like every time they try to send money, the UI sort of shows that they're sending money, but actually just sends to me, and they won't find out for a little while. There's a lot of things where you want to be running the right Bitcoin code, and that's a hard problem, right? Because we're sort of operating in this trustless, decentralized network. How do you get into this in the beginning, right? If it's your friend and saying, hey, here's the Bitcoin I'm running, I know this is good, then it works. But just a website, what if someone hacks the website? Things like that. So it's like a huge rabbit hole, and you can try to worry about it for years. But anyway, you download the binary, assume you've somehow gotten the binary and you're pretty sure it's the right software. So how do you connect to this network? Well, there are these hard-coded DNS seeds in order to find peers in the beginning. If you know how DNS works, it's how you look up IP addresses based on a host name. There are some servers that will return multiple different IP addresses every time you query them. And those are IP addresses of currently running Bitcoin nodes. So the idea is, okay, someone's running a Bitcoin node, they've got their DNS server, you query that DNS server and it will hand you out some IP addresses. This is also sort of centralized / trusted / whatever, in that, if someone compromises these 4 or 5 DNS servers, you might not be able to connect to the Bitcoin network, right? So in practice, it's not completely mathematically secure and trustless. There's all these real world issues. That's like, how do I know I've got the right software? How do I know I'm connecting to the actual Bitcoin network? What if my ISP is blocking me and sending me to some other network? Or things like that. So in practice, it sort of works okay right now. You connect to the DNS seeds, and then you connect to a Bitcoin node, and you ask for headers. And you say, hey, I just showed up. I know about one header. There's a hard-coded header in the code called the Genesis block that Satoshi did. And you say, hey, I've got this Genesis block. Do you know anything that builds above this Genesis block that comes after? And they say, yes, I actually know 500,000 headers that come after it, and they'll start sending it to you. And they send it to you in like a couple thousand of headers at a time, and then you start to download all those and verify them. The header chain, you get it first, and it's actually very quick. You can do it under a minute if you have a good internet connection, and you verify all the work before you do anything else. So this is nice in that the attacker, in order to sort of make you do more work here, would have to do a lot of proof of work. But for you, it's very quick to verify everything. Even 500,000 headers, 30 seconds if you got a good internet connection, something like that. Because all you're doing is 1 hash per header, right? You just download the header, check the bits, check the time, make sure the times are like, progressing reasonably. If the times keep going backwards for like, I think it's 10 blocks, then you consider it invalid. But your computer can actually do this. It's 500,000 hash functions. I'm sure if you've seen for the problem set, you can do that in a few seconds in many cases. So you can verify the work done throughout the entirety of the Bitcoin's existence pretty quickly. So then you've got 500,000 headers, and now you need to actually download the blocks. Okay, any questions about header synchronization? Seems pretty straight up. Yeah.
Can you cache any of that work, since you're going to see some of these every time you sync?
Well, you save it to disk. So you don't have to, like, if you turn your, if you shut your computer off, turn it on the next time, you've already got all those headers on disk. Basically, you save them to disk once you've verified them. So you download a couple thousand, it builds linearly, so it's nice. You like download them, validate, and as you validate, write them to disk. And then when you start back up, they're on disk. You trust your own disk. If someone goes in and modifies things on disk between running of Bitcoin, all bets are off, right? So you sort of implicitly trust that. Okay, so yeah, that's pretty quick, works well. Then you get to the real hard part where you now have to validate all these signatures and download all these transactions. Okay, any other questions? Good? Okay. Okay, so then it's called IBD, initial block download. So you get the headers first, that's quick. Now you start asking your peers, hey, here's this header from 2009, block height 1. Give it, here's the header, can you give me the full block? With, what's in the, I have the header, what are all the things that go into the Merkle root? So you request blocks from peers, you match the transaction list, the Merkle root and the header, and you process each transaction in order, right? So you download it, say, okay, here's all these transactions, let me take the hash of all of them, compute the Merkle root, make sure it matches the Merkle root I see in the header I've already gotten, and now process each transaction. Okay, so what do we do to process transactions? Okay, so you've got this UTXO DB. So this is unspent transaction output. So all the, I'm sure in like 2030 there will be a new slang term where we'll just call money UTXO. It's like, hey, I got a lot of UTXO. I mean, I'm already doing that, and I'm pretty ahead of the time. So, so you've got this database, which is basically a key value store, and it just has transaction ID index, right? So this sort of how you reference inputs in Bitcoin, right? The transaction ID index as the key, and then the value is just the output, right? The script sig and 8-byte amount, right? So it's pretty compact. You've got all these key values, and it's using level DB, but you could use some other key value store database. And the idea is, okay, every time you get a transaction, validate all the inputs, make sure all the signatures are good, make sure it's spending things that actually exist in your UTXO set, and delete those inputs from your UTXO DB. You're saying, okay, this transaction is spending these inputs, so delete. So I guess, first, make sure the transaction's valid, given your current UTXO DB, right? So validate that all these inputs exist. Validate all the signatures are correct. Then you're saying, okay, this transaction is good. Now I modify my database by deleting all the inputs that are consumed and adding all these new outputs from the transaction, right? So this modifies the database in place, and you're sort of constantly, reading from it to validate inputs, and then writing to it to delete inputs, and then writing to it again to add outputs. So it doesn't seem too bad, but there's a lot of disk access, and the UTXO DB is a key value store with a lot of keys. The values are very small. So it's not like a crazy database problem, if anyone's interested in databases and stuff. But it can be slow, and we want to really optimize it. So when you sync the initial block download, you're doing this 300 million times. So there's about 300 million transactions historically. So you're validating signature, deleting input, adding output 300 million times. It ends up being about 170 gigabytes of downloads. And then the end result, when you're done, modifying this database, is that you have 55 million transaction outputs remaining, and it's about 3.2 gigabytes of disk use. So yeah, but you had to download that 170 gigabytes to get to the 3.2 gigabyte end state, right? Because most of the transactions that have been created and most of the outputs have then later been spent, right? So there's a lot of churn. So yeah, of the 300 million, and these are not the same numbers. I was actually looking how many transaction outputs have been created throughout all of Bitcoin, and I couldn't find the number, and I didn't want to, write software to figure it out. But you can certainly figure it out from the blockchain. But yeah, this is transaction outputs. How many total transactions have TXOs? I'm not sure. But yeah, so it's pretty big, but it's reasonable, right? Like we can do this on today's computers. If you've got a decent laptop, this is possible. This total time taken depends on a lot of factors. Has anyone actually done initial block download and synced a Bitcoin node and want to say about how quickly they did it? Or okay, James, how long did it take?
0.15, it's actually quite quick. I mean, on a spinning disk, it will take about 6 hours, maybe.
On a spinning disk?
Yeah, with the new one, it's really quick.
Because I run 0.15.1 on a laptop with a spinning disk, and it'll take like overnight to just sync up a week or so. It's really slow, but I don't know.
Like my hard drive broke, I did it from scratch. I did it in like 8 hours.
Wow, cool. Okay, so 8 hours to do the whole thing. Anyone else have tried it? Yeah?
It took me a week.
Yeah, a while back took weeks. So the software has been improved quite a bit. So if you downloaded it, like I first downloaded it in 2011, and it took overnight to download everything. And the download was vastly smaller. It was less than a gigabyte to download the entire blockchain. So what's interesting is that the time taken for initial block download over the last 7 years has been somewhat constant in that the blockchain gets bigger and bigger, but there's all these optimizations to the code and the databases, and so that sort of keeps pace. Although actually, I'd say recently it's gotten faster, because like 0.15, 0.11 or 12 had a big speed up as well.
They completely refactored the network code. It used to be coupled with the synchronization,
Yeah.
and then they decoupled it. And now
Yeah,
it
I
goes
think that was mostly Corey, right? Yeah. So Corey Fields, who also works with the DCI, helped to refactor the code, make it a lot faster. There's definitely still optimizations. A lot of cool, a lot of it's pretty low level, like tweaks kind of stuff, but some of them are pretty big things that most of the big things, low hanging fruit, has already been gotten. The worry is that long term, this just keeps going up, right? As the blockchain gets bigger and longer, it's going to be harder to validate. It can be parallelized to some extent, but there's also like network I/O concerns, things like that. So it's tricky, but doable. Okay, any questions about initial block download? Good. Okay. So here's a question. You've got this UTXO-DB. What about this 170 gigabytes? Do you have to store it, or can you delete it? This you can't delete, right? So do you think this is okay? Like, yeah, you can maybe delete some of this. Actually, there's a lot of research into maybe we can delete this. Accumulators, cool stuff like that. It would be really cool to have some kind of data structure where we can keep adding these, we can add, remove, and prove that something's, and then, seek and see if something's in there, where it either is like constant size or login size or something like that. That'd be really cool. There are constructions like that, but they don't work for what we're trying to do right now. But there's a lot of research into that. If anyone here finds some cool data structure that you can use for the UTXO-DB that doesn't keep growing, linear size of the number of keys, everyone in Bitcoin will sing your praises forever. And, but it's an active research area. Okay, so pruning. By default, that should be a K, not an M, sorry. There's only 500K blocks, not 500M. Anyway, by default, your client will download all these blocks and store them on the disk. And that's important because what if someone else requests them from you? Someone else, everyone starts out as a noob. Someone else comes and says, hey guys, I just downloaded Bitcoin. What's going on for the last 9 years? And you might want to give them blocks to let them into the system. So you can serve to others who are doing IBD. However, if you want, and your hard drive's smaller, you have an SSD or something, you can prune and delete the blocks after you've done IBD with no loss of security, right? Anyone think of downsides doing so? Not really, right? The real downside is sort of this, right? Well, not everyone can prune, right? If everyone prunes, no new entrants to the system. So it's a little bit of a tricky sort of like seed versus leech kind of problem where someone's got to be there to serve up these blocks. You don't have to trust them, right? You're still validating all the work, validating all the signatures. They can't do anything bad. But someone's got to be there to provide the network capacity. And so it is tricky. Like most of the nodes on the network are behind people's cable modem firewall kind of thing. So you can't actually connect to them and download. And if you run a node that does allow people to connect in and serve them blocks, people will download quite a bit. So I have one in the office over there. It ends up sending out about 3 terabytes a month which is a lot, right? Like it's, dozens of gigabytes a day, 20, 30, I don't know. So yeah, people are doing this. People are connecting in and downloading all the blocks, either through IBD or just keeping up with current transactions. So yeah, pruning is possible, but it's someone, not everyone can do it, so it's sort of an unsolved issue there. There's a lot of research into how we can do partial pruning, where, okay, I'm gonna only store the last month's worth of blocks, which is mostly what people do, because a lot of people have intermittent connectivity, where they'll turn off their node and then start it back up again a few days later, and they just need to catch up with the last few blocks. Okay, so pruning's cool. That's been in since 0.12 or something. So I'll go through, in practice, if you go to your Bitcoin node, what does it actually store? And if you just go to your Bitcoin folder, which in Unix type OSs is like home directory /.bitcoin. Total random aside, I don't like how they put a dot in front of all the really important folders. Right? It's like they hide all the important things, like your GPG folder has got a dot and your Bitcoin folder's got a dot. But like downloads doesn't, and like who cares about that? Anyway, so if you just ls in your folder, here's all the files, and just go through real quick. Here's the files, and I'll describe. So there's a ban list.dat. This is a list of IP addresses that you have banned because they're bad. They're doing something weird. So I'll get to it at the end. I sort of am thinking of making a ban list for the problem set, because there are some nodes that are doing non-good things. That was what caused yesterday's outage. Someone was connecting. Although it was really my fault, because the server code was not verifying inputs correctly. But yeah, in Bitcoin, you verify everything. If people start sending you nonsense data, or they say, hey, here's a block and it's wrong, or hey, here's a transaction and the signatures are wrong, you'll pretty quickly ban them. Because it's like, well, if they're making a mistake, it's a computer. There's no excuse for making a mistake, right? So either their software is just different than mine, or something's wrong with their software or their hardware. I don't know, but they're wasting my time. They're sending me nonsense. Ban. So you have your own ban list. Then the blue ones are folders. I'll talk about those later. Then you have peers.dat, which is good nodes. So it's quite a bit, 4 megabytes. And you keep track of, here's all the different nodes I've connected to for the past, the duration of my, however long I've been using Bitcoin. I keep track of all their IP addresses, how much uptime they've had, what I've downloaded from them. And so, I sort of sort them and put the good ones at the top. And like, okay, here's all the different Bitcoin nodes. So next time I start up Bitcoin, I'm going to try to connect to them. So this makes the network very robust, because everyone remembers everyone else. And then when they need to, if there's a network disruption, maybe half the nodes go off the network, you can still try to connect to the rest. And also peers will share their peers' files. Not directly, but they'll sort of take random samplings of this file and share it with each other, so that everyone sort of knows about everyone else. Okay, then there's a wallet.dat, which is very important, because that's got all your precious UTXOs. And we'll talk about wallets one day, I think. There's a Bitcoin conf, little config file. You can set some settings and things like that. Debug file, which shows all these weird messages, and a mempool.dat. So the mempool is transactions you've seen that you've not seen in a block yet, right? So people are broadcasting transactions, and you store them. It used to be just in memory, hence the word mempool. Now it's more like disk pool, because you actually store them on disk, because it saves a little speed when you shut down and start up again. Okay, so any questions about just what all these files are doing? Okay, makes sense. So now the folders. Chain state, blocks, and database. So any guesses onto how big these things are, based on previous slides? So how big is chain state, for example? Guess? 3 gig, okay. Okay, yeah, 3 gigs. Right, this is the UTXO set. 3-ish gigs. This is all the blocks. What? Oh no. And then database, actually, I have no idea. Does anyone know what that is? There's a database folder, and it's got one little log file, and it's like 80 kilobytes. I don't know what it is. Do you guys know? Okay. Yeah, I don't know. But there's a blocks folder, and that's got all the blocks. And that's your, huge amount of data. And this is the UTXO set. Not too bad. So yeah, you can look in it. It's reasonable, but yeah, it's kind of big. Okay, and now, so any questions about the data stuff? I'm going to go into blockchain as a database real quick at the end. Okay, so it's 186 gigabytes, or alternatively, you can think of it as just 3 gigabytes. But it's a really crummy database. So I've heard a lot that, blockchain is going to change the world, and it's like a database that's shared among everyone, and you can query things. It's a really bad database. So for example, I'm going to have some fun interactive questions where some of these are answerable, some of these are not. So and I'm posing the question to my Bitcoin node. So I pose this question to my Bitcoin node. Hey, remember transaction 9095C3 from back in 2014? And how do you think the Bitcoin node will answer? Will it answer or will it not be able to? Any ideas? Yeah.
Wait, where does 186 gigabytes come from?
183 plus 3. So the total data usage on this computer is 186 gigs. Right, the rest are kind of small.
What do you mean?
So I mean, when you're using Bitcoin, you've got 186 gigs on your hard drive or your SSD devoted to Bitcoin. Right, so you've got this 186 gigabyte database essentially, but it's a really crummy database. And it can't do a lot of the things you might expect it to. So for example, you arbitrary transaction from the past. You say, hey, there was this transaction a couple years ago. Give me the information about it. And what do you think the response from the full node is?
Valid.
What, sorry?
Valid or not valid?
It's valid or not valid? Any other ideas?
What's the header?
Sorry?
What's the header of the block you sent?
It asks instead for a header, okay. Other ideas? Yeah, so sort of that. It'll say, remember TX this? No, it's somewhere in the blocks, maybe, but I have no idea where. It's not in the chain state, right? So the blocks, it just stores the blocks, right? Like here's block, here's this block, here's that block in line. And if you say, hey, there's this transaction, okay, go look for it. Oh, 2014? Well, that might be somewhere in the middle. But yeah, if you don't know what block it's in, forget it. So it does have an index of blocks. It'll tell you a block, but transaction, no luck. Yeah.
So it pretty much tells you if it exists, that's it.
It won't even tell you if this exists. It has no idea.
What's it somewhere in the blocks, so.
I might have made that up. Right? So if you're saying, hey, here's this transaction. Do you remember it? Does it exist? I don't know. So, yeah.
If you query about a certain block, will it be able to?
Yes. And yeah, good question. But I'll get to that. I think it's in the later slides. But yes, if you query it based on a block hash, then it does have that in the database, and it'll be able to get it for you. Yeah, James.
The database directory does that.
You know what the database directory does?
It's the journaling for the other databases.
Journaling for other databases. Okay, I didn't. Yeah, cool. It's very small, so I guess it helps things work. Okay, so this one. Do you know this transaction? No. How about this? Well, I've got this output, right? It's still there in the UTX. Someone spent here. It's like this is a transaction, and the first one. It's an op return output, right? So it's got some extra data, but op return means it's invalid. I can't spend it. Can you tell me what the data is? Do you think it'll be able to? Right? If you query, hey, here's this output. What do you think the response will be? Yay? Nay? Nay? Okay, I'm seeing nays. Yeah. Nope. If it's an op return output, even though it's unspent, well, it's unspendable. So you don't put it in the UTXO database. Because you just see, oh, this output, op return's in there. Don't bother putting it in. No one will ever be able to spend it. So there's no reason to put it in. So op returns are used to sort of commit to data and all these different protocols. But the actual normal code won't store them. Okay, anything else? Next one. This one. Hey, I have a public key, and here's the hash of my public key. This is essentially an address. So we didn't talk about addresses, but the Bitcoin addresses that start with like a 1 and then have these alphanumeric stuff, it's just a different encoding, slightly shorter than hexadecimal for a pub key hash. So you say, hey, I've got this, I have a private key. I just computed the public key. I hashed it. I got this. Do I have any money? I think I did. I don't remember, but I remember my private key. I backed that up. That was the important part, right? Everyone says, keep your private keys. So I have my private key. But all this, data and all this blockchain stuff, I lost my computer, but I have my private keys. I got my money. How many coins do I have? How many outputs? What do you think the full node will tell you? Yeah. Any ideas? It'll say, I don't know. Well, you're going to have to search through everything in chain state. And it doesn't index based on the public key script, only the transaction ID index pair, right? It's a key value store, and the key is this 36-byte TXID index. So this is a very real problem, right? Like, okay, I backed up my key, or I took my private keys to some other computer or something like that. And this is it's gotten a lot faster. It used to take hours, right? Where you had a hard drive and you're like, okay, import a key to this wallet. And it's like, well, when did you do transactions? It has to look through the entire blockchain linearly to see if any of these transactions have an output that matches that. And then says, oh yeah, you got money back in 2013. Oh, then you spent it. Or then, and sort of replays things because it doesn't have an address index. Okay, next one. This is an example. How many coins? So you say, hey, here's this output, this transaction, :1. How many coins does it have? Will the full node be able to tell you this? Yay, nay? Seeing a bunch of nays. No, it will. Yeah, this is the one thing it can do. So if you say, hey, 7434 :1, it'll know that. That's in the UTXO DB because that's the key that the UTXO DB sorts by, right? So yep, this is a UTXO. It's unspent and it has a bunch of coins. And this is fairly recent. I was just looking through. Someone got a couple $1 million worth. Cool. Is that a million? Man. Okay. Yeah, it's in the UTXO set. Hasn't been spent, and you can sort quickly based on TXID index pair, right? So I think this is in some software called an out point, where it's like you concatenate them, and it ends up being 36 bytes, right? This is 32 bytes. This is 4. So you sort of have a 36-byte out point, which describes what goes into the UTXO database.
But once it gets respent, it's hard to find again.
Yeah, once this is spent, you delete it from the UTXO, and you won't remember it anymore. It'll just be, hey, do you know how many coins does this have? You're like, well, you can still answer it. You can say none, right? If it's spent, and you say, hey, how many coins does this guy have? None. It's not in the UTXO set. Which was, yeah. So the previous one, I just copied these randomly. Okay. Okay, so any questions about what is stored and what is not stored? Wait, let me. Basically, keeps track of UTXOs and it keeps track of historic blocks in order to give them to people. And it keeps track of the headers. The headers ends up being small. All the headers total is like what, 40 megs? Something like that. So yeah, you can add further indices, right? You could write software to answer all these questions very quickly. But that's not what Bitcoin does by default. Those types of indices would take a lot of extra space and add a lot of CPU work, things like that. So a very common thing is an address index. So people can ask if they have any money. So the second to last one where you say, hey, I have this key, key hash. Do I have any money? Do I have any transactions? Having an address index is actually pretty useful for a lot of things. For example, importing keys or like web wallet kind of things. But Bitcoin by default doesn't do it because, well, why? I mean, you can make arguments that it would be actually useful to have in the normal code, but we don't. Okay, any other questions about what indices, what it can do, what it cannot do? Somewhat counterintuitive in many cases, where you say, hey, here's this transaction, and you can't actually find it. Or you have to scan through 180 gigabytes in order to find it. Yeah. So wait, James, I have a question. So how big is an address index for you were working on?
Usually equal to the size of the chain itself.
Wow. So it could be hundreds of gigs. Yeah. Yeah.
At least with Bitcoin, it takes usually multiple weeks to generate.
Weeks to generate. I bet you. Well, okay.
Well, Electrum usually takes a few days, and Insight, which is popular one, takes weeks.
Weeks. Okay. Well, that's. I mean, so the other thing is these are like fairly involved sort of CSE software engineering problems, and optimization really works, right? If you download like Bitcoin 0.9, it'll still work, but you're never going to catch up. Maybe not never. I don't know, if you have a fast computer, but it'll take, months and months. And as people have been updating the software and making it faster, making it more efficient, now it's quite fast. And you can, sync the whole thing in a few hours on a good computer. So address index is one of those things where it hasn't had like the full force of all these Bitcoin protocol coder people on it. Because it's sort of seen as like, well, yeah, that's kind of a fun feature if you want, but it's not like a core utility of Bitcoin. Okay, so yeah, maybe, it is a database, maybe not the best way to think of it though. Don't think of the blockchain as like a global shared database, because it sort of is, but it's a fairly specific database that isn't useful for many other things. Yeah, and it's also untrusted. Another part of why is it's untrusted, right? Most of these things exist so that they can be used over the peer-to-peer network, right? If you request a block, I'll give it to you. If you give me a transaction, I'll match it against my UTXO set. But an address index doesn't work that way. It's sort of trusted. I can easily omit things, right? If you say, hey, I've got a key, what are the transactions involved with this key? I can omit things very easily, and there's no way for you to prove it or verify it. So your DB queries aren't really given out to network peers. And network peers are scary, and you need to ban them if they act funny. And this happens all the time. If you look through Bitcoin logs and you have a node that's up, every few seconds you're going to be disconnecting from someone or banning them because they're doing something crazy, trying to hack into you or whatever. So basically, all you're doing is you're providing headers, blocks, transactions, and you're sharing the other IPs of nodes. You try to simplify it. Okay, other questions? Yeah, bad database, good for consensus. It kind of works. Everyone's got the same UTXO set. Even though they all really would like to change that UTXO set. I would much rather everyone had a UTXO set where I had those 273 coin UTXO. So almost everyone in the systems would rather there was a different UTXO set, and yet they all managed to agree on a single UTXO set. So pretty cool.